Yeah, welcome. The topic we'll be discussing in this lecture is about buses. So already we have discussed about buses at several places, right? So generally buses represents the communication channel. So it is the communication channel which connects the processor, main memory and IO devices. All these are interconnected by means of a bus. And there are some certain set of rules which govern the behavior of the bus, like who should access the bus at a given time and what signals they can transmit. All these are governed by set of rules. These set of rules are called as bus protocol. Okay. So in this lecture actually we are going to discuss in detail about the way in which the system bus works. Okay. So as we already know, when we say bus, it includes all these three buses, or we can say that it includes all these three lines, which are data lines, address lines and control lines. So address line is used to specify the address of the memory location from which the data should be read or data to be written. Or address may refer to IO devices also, because we have learned that IO devices were also will be given some addresses. Okay. So this address may refer to either memory location or it may refer to IO device. Data refers to the actual data that is to be either read from a memory location or returned to a memory location, or read from an IO device or returned to an IO device. Okay. Control signal, generally it represents the read or write operation. What is the operation you want to perform? Generally these are the two control signals. Either it can be a read operation or a write operation. Control signal may also specify the size of the operand. Operand in the sense data. What's the size of the data? Whether the data is represented as byte or word or long word, whatever it may be. Okay. Again, the word size varies with computers, that we already know, right? So it's at the top level you understand that the control signal represents the operand size, and the control signal also includes timing information. Okay. Actually, this is crucial with respect to this lecture. So in this lecture, we are going to concentrate more on this timing information. Okay. So timing information means like who should access the bus at a given time, and what they can do, what operation they can do on a given time. That is called as timing information. Okay. Fine. So, so there are based on the timing of data transfer, based on the schemes of timing of data transfer over a bus, the bus can be classified into two types. One is called as synchronous bus, the other one is called as asynchronous bus. Okay. So this classification is actually based on the timing of data transfer. Okay. Right. So we are going to discuss bus under two headings. One is synchronous bus, the other one is asynchronous bus. Fine. So first we'll be discussing about synchronous bus. Okay. See, primarily in a synchronous bus, there will be a clock. There will be a clock which governs the bus. Okay. See, this clock is different from the processor clock. Processor clock will be operating at a very high frequency. Okay, high frequency means, for example, you see this clock. This is the one cycle duration. Okay, one cycle duration is generally one positive and one negative. Okay, this in case of an whether it's analog or digital signal. Normally in system in computers it's a digital signal. If you take an analog signal, this is one cycle. Okay, this is one cycle, one positive, one negative. So the same thing here also, but it's a digital signal, one positive and one negative. So this duration, you see, this duration, say let us call it as this duration cycle time, this bus cycle duration, let us call c naught. Okay, there may be another signal which is something like this, which is half of this signal. This signal duration is c1, let us say. Okay, this is also one clock cycle, because one clock cycle is what, one clock cycle or one bus cycle. One cycle is what, it is the duration of one positive pulse and a negative pulse. Okay, but this signal we say that it is a it is a low frequency signal. This signal, compared to this signal, we say that this is a low frequency signal, whereas we say this is a high frequency signal. Okay, so I'm just trying to I think probably you know already. I'm just trying to make you understand what is a high frequency signal and what is a low frequency signal. Okay, so if this clock cycle duration is high, then it becomes a low frequency signal. If this clock frequency duration is low, then it will become a high frequency signal. Okay, so if the time is reduced, so this is time, right? This is time. Okay, x-axis, this is time. So for one cycle it is taking this much time. If the time is reduced, then we say that it is a high frequency signal. Okay, fine. So what I'm trying to say in the sense, this clock, so in a synchronous bus, the bus will be governed by a clock. Okay, this clock is different from the processor clock. The processor clock will be a high frequency clock. That will be operating at a very high frequency, because inside the processor all the device can operate at a faster rate. But system bus is not a high frequency clock. It is comparatively low frequency, because system bus has to communicate with diverse devices like memory, IO devices, and you cannot expect the IO devices or different IO devices to operate at a faster speed. Okay, so this clock is different from the processor clock, right? Okay, so the core point is a synchronous bus works based on the clock. There will be a clock which controls the bus activities. Okay, or based on the clock only the bus will work. Such a bus is called a synchronous bus. Okay, so let us discuss this with an example. See, this is the bus clock. Okay, this is the bus clock. Okay, based on the bus clock we understand the timing. Okay, so this is just one clock cycle. This is just one clock cycle. Okay, so the basic idea of synchronous bus, what it says in the sense, all operations should be completed within one clock cycle, right? The basic idea of synchronous bus is that all operation should be completed within one clock cycle. All operation means what? I mean, the typical operation is what? Either it is a read operation or a write operation. Whether it is a read operation or a write operation, it should not take more than one clock cycle. It should not take more than one clock cycle. Accordingly, the clock cycle is designed in a synchronous bus. Accordingly, this is such a way that the communication between no any two devices will not take more than one clock cycle. In that way, it is designed. Okay, right? Fine. Uh, so, so we will learn that in detail as the lecture proceeds. But as of now, you understand that when a read or a write operation happens, it should complete within one clock cycle. That is what the basic version of synchronous bus expects. Okay. So this is the bus clock. Okay. And somebody will be the master of the bus. Okay. Bus master we have discussed. So the bus master is the one who owns the bus, who can initiate some data transfer on the bus. The device which can initiate a data transfer on the bus is called as bus master. Who can be the bus master? Either processor or any DMA controller can be the bus master, not anybody else. Okay, the bus master should be either processor or DMA, any of the DMA controller. Your system may have more than one DMA controller, so any of the DMA controllers can be the bus master. Okay, for simplicity, let us assume that processor is the bus master. Let us assume that processor is the bus master. Okay, now this is actually this clock diagram. It shows like how a read operation is performed using synchronous bus. How a read operation is performed using synchronous bus. Here read in the sense, reading from IO device. Okay, how the processor or the bus master, how the bus master read something from IO device. Okay, we are assuming the bus master as the processor. Okay, so this clock diagram, uh, this I mean this diagram, basically it shows like how the what you call uh, how the processor reads something from the any of the IO device using synchronous bus. Okay, fine. Okay, so let us see. So here everything, it is based on the clock. Okay, so at time t naught, So this is the rising of the pulse, right? The pulse is going at the higher end. Okay, at time t naught, the bus master, that is processor, is placing the address and the command in the address and the command signal. Okay, here we assume that address and command signal are specified through a single bus. Okay, so the processor is placing the address. Whose address it is placing? It is placing the address of the IO device from which the data should be read. Processor wants to read something from the IO device. Okay, so it is placing the address of the IO device from where it want to read some data. And command in the sense, what operation it want to perform. What operation it want to perform? Read operation. So address will be placed in the address bus and command will be placed in the control bus. Okay, these two signal it places, right? Okay. Once processor places this two information, this will be available to all IO devices. Okay, not only one IO device. There are, if the whatever the IO device available in the computer, to all the devices it will be available. Okay. Now every device will compare. It will take this address, whatever the address given by the processor, it will take that address and it will compare with their address. Every IO device has its own address, right? So it will compare whether this command is supposed for me or not. Am I supposed to perform this operation or not? So like that they will compare. So say let us assume there are four devices in your computer. So this address will be uh, the, I mean all the devices will get this address. Device 1, device 2, device 3 and all the four devices will get this address. Let us assume this address actually refers to device 3. So device 1 will check whether it is matching with its address or not. No. Then device 2 will check whether it's matching with its address. No. Device 3 checks whether it is matching with its address. Yes, it's matching. Device 4 will check it's not matching. So if it is not matching, that respective device it won't do anything. If it is matching, in case of device 3 it is matching. Okay, let us say the device 3 address is 011. Okay, let us say this is 000. Okay, so this is 00, this is 001. Okay, this is 010, right? One minute. Anything can be the address, just for understanding. This is okay. Here I'm writing. This is 001. Okay, this is 00 010. Okay, this is 010. This is 010 and this is 011. Okay, right, and this is 100. Okay, now in our case it is matching with this. So this device, what it will do, it is matching, then it will, okay, so whatever the instruction the bus master is giving, it is for me, like that it will understand. Okay, so it will understand and it will then it will check the control signal. What is the control signal? It is a read signal. Okay, it says that I want data from this IO device. Okay, so then this device will, whatever the data it has, so probably the processor is asking means it will be having some data, so its data will be available in the data register. Okay, that data it will place in the data bus at time t1, at time t1. Okay, so why this much gap? Why it is taking this much gap? In the sense, during this time, all the devices should check whatever the IO devices in the computer. How many maybe the IO devices are available in the computer? All the devices should check whether this address is whether this address represents their address or not, and the respective IO device should. So the IO device is called as slave. Okay, and the bus master is called as master. So the addressed slave, then it will place the data on the data lines. Okay, so this time should be that much enough, sufficient enough. Okay, because if all IO devices were unable to check during this time, then there is no use. Okay, then there is no use, then the purpose may not be served. So this time is designed in such a way that it should be that much sufficient, that all the IO devices should be able to check their addresses and the addressed slave will be placing the data on the data lines. Okay, fine, right. So see here, one important thing you should understand, Uh, Even say for example, assume that D3 has identified that this data, I mean D3 has identified that uh, the the processor is actually giving the instruction for it only. D3 has identified at this time itself. Assume that D3 has identified at this particular time itself. But even then D3 will not place the data immediately. It will wait till T1, then only it will place. Okay, why? Because means everybody should check, and they should also confirm. Then only it will place. Okay, or forget about confirming all the thing. The synchronous bus, it is working based on this timing only. It is based on this timing only. Okay. Actually D3 does not know whether everybody checks or not. Everybody checked or not. But at time T1, it is ensured that everybody will be checked by that time. They no need more than this time. Okay. It is something like an upper bound. Say for example, you want to say you want to travel from college to say Mehripatnam. Okay, so what is the upper bound? Upper bound is maybe 1 hour, but sometimes you may also reach within half an hour. Okay, so this is also something like that. This is the upper bound. So actually the addressed slave will not get any information whether everybody checked or not. All those things it don't know, but it will, if it knows that I am the one who should respond. It may know at any time. It may know immediately here or immediately here, but it is sure that it will know before T1. That is sure. Okay, any device will know it before T1. Okay, then exactly at T1 it will place that data. Okay, okay. So this is the crucial thing you should understand with respect to synchronous bus. Everything is working based on this timing only. Everything is working based on the timing only. Now, now the addressed slave has placed the data on the data bus. Okay. Now the data is available. See, data is available at T1 itself. T1 itself data is available on the bus. But master will store the data on the data lines into its buffer at T2 only. Okay, again, why this timing in the sense? Why this gap in the sense? So T1 at T1 the data is available. Okay, but immediately once so processor will be also guessing now. CPU, say let us assume processor is the master of the bus. Okay, bus master. So the processor also will be guessing that data should be available. So by that time, at from T1 onwards, processor will start setting the input buffer. It should set the input buffer. So to set the input buffer, this much time is given. Okay. Again, for example, processor may complete setting up the input buffer at this time itself. Okay, but that doesn't mean that processor will take the data at this time. No. Okay, processor may complete setting up the input buffer at this time or at this time or at this time, any time. That is not an issue. But again, this is the upper bound. This is the upper bound required for the processor to set up the input buffer. So it was calculated that there is no reason for the processor to take more than this much time to set up the input buffer. Okay, so this upper bound is given. So now also processor does not know, to be frank, processor does not know really whether the data is available or not. All those things it does not know. By T2, it will assume that data is available and it will start reading data from the data bus and it will be storing it in the data, I mean input buffer. Okay, so that process is called a strobe. Master strobes the data on the data lines onto into its input buffer for a read operation. Okay. See, the crucial thing here you should understand is everything will work based on the time. Okay. See, it is something like what you know. Say for example, say there is no mobile phone. There is no mobile phone. Okay. Say say your friend is telling that he is coming from Delhi by train. Okay. Say maybe it takes 2 days. Okay, and you should go and pick up. Okay, so on based on what you will work based on time, right? So he started there. If it is on today, that is 1st of April. So at this time, so he will be reaching Hyderabad maybe 3rd of April at this time. Okay, So you will be reaching the railway station at this particular time around 6:30 or whatever it may be to receive him. Okay, so on what basis you are working? You are working on time. Okay, because there is no other way for you to communicate. Are you getting? So this also works like that. Okay, so this also works like that, but it is working based on the upper bound. Okay, it is not that. See, for example, here T1. I mean, this uh, data should not be placed before T1. So why it is not placed before T1 in the sense uh, that is the upper bound. Why upper bound? Say why we should work based on upper bound? Because we need a common clock to control all the device. We need a common clock to control all the device. See again I will tell one more example. Assume that we have two devices, device 1, device 2. Say that device 1 works at a very faster speed, whereas device 2 acts in a very slower speed. Okay. Now, once the address and the command is placed at time t naught, device 1 may identify this address and it will recognize that it is for this, and it may be capable of keeping the data in the data bus at this time itself. Are you getting? But device 2 is very slow. It can identify this only at this time and it can place the data only at this time. Okay. Okay, right? Now the question is we need a common clock to control all the devices. So here I have given two devices, but there may be n number of devices. Different device may work at different speed. Device 3 may identify and place the data, may be able to place the data at this time. Device 4 may be able to place the data at this time. So different speed, different devices working at a different speed. But we need what? One common clock to control everything. So we have to work based on this common clock should be set up based on which device? Based on the slowest device. Are you getting? So this common clock should be set up based on the slowest device, so that it will ensure that all device can satisfy the criteria. All device can satisfy the criteria. Okay. So based on the slowest device, these timings were fixed, right? So at T naught, the bus master will place the address and the command signal. At, uh, by T1, whatever may be the device, whether it is the fastest or the slowest device, will be able to recognize the decode the address, and it will understand what is the operation to be identified, and the addressed slave, if it is a read operation, will keep the data in the data bus. Okay, right? And in spite of again whether how much time it requires for the master to set up the input buffer, this is the upper bound. It won't take more than T2 minus T1 times. Okay. At T1, the data should be available in the buffer, so the processor will store the data onto the on the data lines into the input buffer. Okay. So this is the overall concept. So this timing diagram actually it explains about the read operation. In case of write operation, so read operation means processor want to read from the IO device. In case of write operation, the master, that is the bus master, places the data on the bus along with address and command line. Command. Okay. So not only address and command, the bus master will also now place the data. Okay. The bus master also will place the data. Okay. Right. So this data will be available in the bus master. How long it will be available means it will be available up to T2. The slave should store the data into its buffer at T2. So the data will be available this much time at till T2. T2 is the your entire clock cycle duration. Okay. So do, and now again you see for the what is the maximum time for the slave to identify who is the device who should read the data. I mean who is the device who should take the data. I mean the data should be returned to which device. Again it will take this much time. Okay. So by T1 it is sure that the slave will identify that I am the particular device who has to this data is supposed to reach. Okay. Then 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 the identified slave will store the data into its buffer. For that this much time is given. Okay. During this time the data will be stored into the slave. During this time, it is used to identify all the devices should check whether the address, whether this task is for them to perform or not. Okay, right. So this is the basic working mechanism of synchronous bus. Right. So this is whatever we have discussed. What is T1 and T0? T1 T0 is this particular time. Okay, this particular time. So this timing is what? It includes the maximum propagation delay between two devices. Two devices means what? The bus master and the IO device. Okay. It also includes the time taken by all the devices to decode the address and control signals so that the address slave can respond at time T1. Okay. So actually that T0 T1 minus T1 is actually based on the speed of the slowest device. Right. Similarly, what is T2 minus T1? Again, it is the maximum propagation time of the bus plus setup time of the input register of the master. Okay, how much time it takes for the master to set up the input buffer. Okay. See, propagation delay means what? There will be some delay in sending the data. For example, the device is sending the data, it starts sending the data at time t naught, but to appear in the bus, it may not appear immediately. It may appear at time t naught plus alpha. At time t, some small delay will be there. Are you getting? Okay. Similarly, say or this is the propagation delay of the bus. This is called the propagation delay of the bus. That is, the device has kept the data. The device has started sending the data at time t naught, but exactly at t naught it is not appearing on the bus. It is appearing with a little delay. Maybe the delay may be by millisecond, but still it's a delay, right? So this is called as propagation delay of the bus. Similarly, there is a propagation delay between two devices. Say device 1 is sending data to device 2. So device 1 started sending data at T naught, but device 2 may not receive immediately. It may receive after maybe T naught plus alpha or beta after some time. So this is called as propagation delay between two devices. This may happen because of the distance between the two devices, or it may happen because of the communication channel. What type of channel you are using? Some channel may be very fast, some channel may be average, some channel may be slow. Okay, right? So T2 minus T1, it also includes the propagation delay plus the setup time of the input buffer register of the bus master. Okay, right. So there is a, see actually in this first timing diagram, whatever we have discussed, here we have not shown the propagation delay and all. See, you see here it is said that the bus master is keeping the address and the command bus address and the command on the address and the on the address bus and the control bus at time t naught. Then immediately it is shown that it is available at time t naught, but that may not happen. It may arrive with a delay, okay. So this is actually an ideal timing diagram. This is to understand the working at a conceptual level, but reality is not this. Reality is there may be some delay. Okay, for every communication there will be some delay. So this is the another timing diagram of the same concept. It is explained with delay. It is explained with delay. Okay. So this timing diagram is divided into two parts. One is the master part. In the master end, what is happening with respect to delay, and how this delay is seen by the slave. That in both the ways it is shown. Okay. So this timing diagram has two parts. One is with respect to the bus master, and one is with respect to the identified IO device, which is the slave. Okay. Right. But the working philosophy is same. Initially, what the bus master keeps the address and the command in the address and the control bus. Okay. So at T naught, the bus master is keeping. You see here at T naught, the bus master is keeping the address and the command in the address and the control bus. But it is not appearing immediately. You can see here, it is not appearing immediately. In the previous diagram, if you see, it is shown as if it is appearing immediately. So as I already communicated, this is the ideal case. This is not the reality. But in reality, there will be a propagation delay. So it is actually not appearing. It is not appearing in the bus immediately, even though the bus master is keeping the address and the command at this time. It appears with a little delay. It appears in the address and the control bus at time TAM. TAM. Okay, right? So A represents address. Okay, A represents address and command signal. M represents master. At master, it is master is able to see the address and the command it placed in the address bus after a little gap of TAM, after a little time gap of TAM. Okay, but if you see the slave is not able to see the address and the data at TAM also. Are you getting? Because slave is somewhat it is not close to the master, right? Master is the processor. Slave maybe away from the processor. It's IO device, right? So and also we don't know what type of communication channel is there between the master and the slave. So in the slave is able to see this only after the time TAS. TAS. So the slave is able to see the address and the control signal at this time. S represents slave. Okay, TAS time. Are you getting? So this is called as what? So this propagation delay is called as the propagation delay of the bus. Because master is keeping at this time, but it is not immediately appearing in the bus. It is appearing with a gap. So this propagation delay is called as bus propagation delay. Whereas this propagation delay is called as device propagation. Master is one device, slave is another device. Between them there is a propagation delay. Are you getting? Okay. Now at this time, all the slaves or all the devices were able to see the address and the command. Then they will decode. Then they will decode the address and they will try to understand like whom this address is meant for. Okay. To somebody this address will be meant. Okay. Let us assume it is a read operation. So it is meant for one of the IO device. So that IO device is the slave and that IO device recognizes that I am the one who has to send the data because it is a read operation. Okay. So at T1, so it's as we discussed, everything works based on timing. Okay. At T1, this particular IO device, it keeps the data on the database. But again, you see the data is not appearing on the database immediately. It is appearing with a delay of TDS. D represents data, S represents slave. So in the slave end itself, there is a delay. So again, this delay is bus propagation delay. Okay, whatever you keep on the bus, it may not appear immediately because something bus may have to initialize, set up, or some process may be there so that this delay is happening, right? Okay, and again, data is placed at this time, but still master is unable to see the data at this time. You can see here, master is able to see the data on the data bus only at time TDM. So this delay between TDS and TDM is called as the device delay, right? Right? Now the data has reached the master. Okay, but again master will not read it immediately. As we know, master will set up the input buffer. Everything works on timing, so master will start reading the data at time T2. Okay, so slave also know that master will be reading only at T2, so immediately slave will not remove the data. After T2 also you see data is available. Data is available. Okay, after T2 also sometimes data will be available. Okay, so here it is more because here it is starting here only. So this is again the propagation delay. So this time here is this time. Are you getting? It's a delay, right? So after a specific even after T2 also after some times only the slave will remove the data from the data bus. Okay, right? Once the data is removed from the, I mean, see, first, okay, before the data is removed from the, yeah, the data also will be removed from the database and also the address also will be removed from the address bus by the master. Okay, so after some delay, both will happen. The bus master will remove the address from the bus, address and the control signal, and the slave will remove the data from the data bus after some times of T2. Okay, so this is the reality. Here if you see all those delays were not shown. Here it is shown at strictly at T2 this address is removed from the master has removed the address. Strictly at T2 the slave has removed the data, but that is not the reality. Okay, after T2 also a small time gap will be given. After that only the master will remove the address. Similarly, the slave will also remove the data after the gap only. Okay, right? So this basically it has shown how the things works with propagation delay. Okay, fine. So this is the basic working principle of synchronous bus. But there are certain drawbacks with this technique. Okay, what are the drawbacks in the sense? Actually, everything is so here the objective in the basic synchronous bus is everything should be completed in one clock cycle. This is the requirement. As there is a requirement that everything should be completed in one clock cycle, I mean one data transfer, either read or write operation should be completed in one clock cycle. Because of that, we are forced to operate at the speed of the slowest device. See, as we have already discussed, some device may be able to decode these address at a very faster rate, but still they cannot respond until T1. They have to wait until T1. Okay. Similarly, sometimes master may set up the input buffer earlier, but still it cannot read the data. It has to wait till T2. So all these are the bottlenecks. Why these bottlenecks work comes in the sense because we want either read or write, it should be completed within one clock cycle, and for every operation it should be completed within one clock cycle. Because of that we are extending the clock cycle. Because of that we are extending the clock cycle to ensure that the slowest device can fit into the clock cycle. So this is the drawback with this technique. Okay, the data transfer has to complete within one clock cycle. This is the drawback. Clock period T2 must be such that the longest propagation delay on the bus and the slowest device interface must be accommodated. So this is the drawback. Clock period T2, that is T2 is T0 to T2 is the clock period. If you remember, this is one clock period, T0 to T2. Okay, this is one clock period, right? So this time should accommodate what? Longest propagation delay. Again, the propagation delay may be different for different devices. The slowest device will have the longest propagation delay. Okay, on the bus, and the slowest device interface must be accommodated. This forces all the devices to operate at the speed of the slowest device. Okay, because of this, what happens? Even the fastest device also working on the speed of the slowest device. Okay, here actually processor does not know, processor or the bus master does not know what is really happening. Processor just assumes that the data are available at T2. Okay, right? See, as we have already discussed, processor even does not know whether the data is really available or not. Processor just assumes that data is available at T2. Okay, it is something like you are assuming that your friend is started at 2 days before Delhi, so he will be arriving here after 2 days. Maybe something might have happened. He might have got down between somewhere, but all those things you don't know, right? So this is also something like that. Processor just assumes that the data are available at T2. Okay, in case of a read operation, or a read by the device in case of a write operation. Okay, in case of write means it is reading by the device. Okay, so so at T2, if it is a read operation, processor assumes the data is available at T2. If it is a write operation, the IO device assumes that the data is available at T2. Okay, sometimes there may be some error might have occurred. What if the device is actually failed and never really responded? All these things processor does not know. Okay, so these are the drawbacks with this particular technique. Okay, so we are making some improvement on the synchronous bus style, that is called as multiple cycle transfer. That is called as multiple cycle transfer. So as the name itself says, multiple cycle transfer means now there is no restriction that the operation, the read or the write operation should be completed within one clock cycle. It may take more than one clock cycle also, right? It can take more than one clock cycle also. Okay, okay, so and also, so not only that, we are also going to introduce one control signal. So there are two drawbacks here. One drawback is all the devices were forced to operate at the slowest device because of the requirement that everything should be completed, the data transfer should be completed within one clock cycle. Okay, the second drawback is really whether the read or the write operation was successfully done or not, processor does not know. They just work based on the timing. At this time this should have happened, at this time this should have happened, accordingly it works. So these two drawbacks we are going to remove from synchronous bus. Okay, to remove the first drawback, we are removing this restriction. What restriction? That things should be completed within one clock cycle. That restriction we are removing. So it is called as multiple cycle transfer. Okay, and the second is we are going to introduce one control signal. We are going to introduce one control signal so that the processor or the bus master will know whether really the operation, whether the data transfer has been completed successfully or not. Okay. So this control signal basically it serves two purposes. One is it informs the master that the slave has recognized the address and it is ready for communication. Second is it is to adjust the duration of data transfer operation based on the speed. Okay. Now different devices works on different speed. Okay. So if some devices is working at a faster rate, then this control signal will help the processor to understand that okay, this device has responded fastly. I can take the data immediately, like that. If some devices takes more time to respond, again that also the processor can recognize to the control signal. You getting? Okay. So these are the two improvements we are making. Okay. Now as we are introducing multiple cycle transfer, now we are going to use a high frequency bus clock. Okay, previously we are using a low frequency clock because the clock should be able to accommodate the slowest device, because we want to complete the data transfer within one clock cycle. But now that requirement is not there. You can take more than one clock cycle also. You can take more than one clock cycle also. So now we are increasing the frequency. Increasing the frequency means we are reducing the time. We are reducing the time. Okay. High frequency bus clock is used. Data transfer can span over several clock cycles instead of just one clock cycle as in earlier case. Okay. So these two improvements we are making. One is introducing a multiple clock cycle with high frequency clock, and the second is by introducing the control signal. Right? Through this control signal, the master will know that when the slave is ready, and the faster device can respond fastly and slower device can respond slowly. Okay. So let us see how synchronous bus with multiple cycle transfer works. So here you can see the clock signal. It is taking multiple clock cycle to complete one operation. But now the clock cycle duration is less, which is called as high frequency clock. Okay. Previously, if you see, it is only one cycle. Okay. Right. Okay, so other than that, everything is same only. The working is same. See, initially the bus master is keeping the address and the control information in the address bus and the control bus. Control bus can also be called as command bus. Now the address bus and command bus are shown in different lines. Previously it was shown in the same line. Okay, that doesn't matter. Okay, so the processor is keeping the address and the command in the address bus and the command bus at this time only, but it is appearing at this time with the propagation delay, okay, right, right. Now as soon as the address is available in the address bus and the command is available in the control bus or the command bus, all the devices will start reading the address and they will try to understand whether the address is intended, whether the operation is intended for them or not. Okay. So one of the device is supposed to perform the operation. Okay, that device is called a slave. Now that device will not just send the data. Before sending the data, it will activate a signal called slave ready. So this is the control signal. We said that there is a control signal, no? So this is the control signal. The slave first it activates the slave ready signal, which means that I am the one who is supposed to send the data and the data is ready. Like that it will communicate. Okay. So all IO devices compares their addresses and one of the IO devices will identify. Okay. And that device will fetch the data and it is ready to send. So before sending, it activates the slave ready signal. Okay, it activates the slave ready signal, but it is appearing with a propagation delay. Okay, slave places the data on the bus and asserts the slave ready signal. So not only it asserts the slave ready signal, it also places the data. After placing the data in the data bus, it asserts the slave ready signal. Are you getting? Right? So this is actually it is placing the data at this time, and also it is asserting the slave ready signal at this time, but data is appearing in the data bus with a delay, and it is slave ready signal also asserted with a delay. Okay, right? Now master is able to see that at this particular time. Master is able to see that at this particular time, because master should also set up the input buffer, right, to read. Okay, so it takes this much time for the master to arrange the input buffer. Now master stores the data. Okay, master stores the data. Master started storing the data at this particular time, but still it may take some time for storing the data. Storing means moving the data to the input buffer. So the data is still available after this third clock cycle also, still sometime it is available. And slave ready signal also active after this also for a period of time, for, for some few time. Okay, right? So once master completed this, what do you call, transferring the data to the input buffer, then the master will remove the address and the command from the address bus and the command bus. Okay, right? And then the slave also will remove the data from the data bus, and slave also will deactivate the slave ready signal. Right? Okay. So this is the improvement which is done on the synchronous bus with multiple cycle transfer. Okay. So that's it about synchronous bus. The next thing we'll be discussing is asynchronous bus. So in asynchronous bus, there is no clock signals. There is no headache of clock signal. Actually, synchronous bus it works fully based on clock signal only. Whether it is multi-cycle transfer or single cycle transfer, it is controlled by the clock signal. But here there is no clock signal at all. Rather, it works on a different technique by using a handshake signal between the master and the slave. Okay. So there are two handshake signals. One is called as master ready, the other one is called as slave ready. There are two handshake signals. One is called as master ready, the other one is called as slave ready. Master ready signal will be asserted by the master to indicate that, master in the sense bus master, which can be a processor or a DMA controller, to indicate that it is ready to participate in a data transfer. Okay. Similarly, slave ready signal will be asserted by the slave in response to the master ready from the master, that I am also ready to participate in the data transfer, like that. First master will assert the master ready signal. Okay, then the appropriate slave will, it is not any slave cannot participate, right? The slave whose address is matching, they should participate. Okay, so that particular slave will assert the slave ready signal. Okay, fine. So the data transfer using handshake protocol, how it works, let us see briefly. So first, as usual, master will place the address and the command information on the address bus and the control bus or the command bus. After placing the address and the command information on the bus, master will assert the master ready signal. That is, it will activate the master ready signal. Now all the devices on the bus will decode the address. As usual, the working style is same only, but there is no clock involved here. All the devices on the bus will decode the address, like whether this command is meant for them or not. So one of the device will identify. So that is the addressed slave. The addressed slave will perform the operation. Whether it is a read operation, read means it will take the data from the IO device and it will keep in the data bus. Write means it will take the data from the data bus and it will keep in the IO device. Okay, writing means it should write into the IO device. Okay. After the operation is completed, it will assert the slave ready signal, saying that I have done with the job. Okay, now master will remove all the signal from the bus once the slave ready is asserted. Okay. Before that, for example, if it is a read operation, master will also store the data. If the operation is a read operation, then master also stores the data into its input buffer before removing the what you call slave ready signal. Okay. So this is the general working flow. Fine. So whatever we have discussed here, that is shown using a timing diagram here. So at first, the master is keeping the address and the command in the address bus and the command bus. Okay. Then it asserts the master ready signal. It asserts the master ready signal after a gap. It is giving this much gap. Okay. Okay. So it is, why it is giving this much gap in the sense. See, generally, actually, it is not required for the uh, actually it is not required for the IO devices to. It is not that the IO device will check the compare their address with their address only if master ready signal is asserted. Even if it is not asserted also, if any IO device saw some address here, if any IO device sees some, if any IO device is able to see some address or some command here in the address and the command bus, they will start comparing. They will start comparing. Okay, but But one thing should not happen. What in the sense? First the master ready signal comes and then the address and the command comes. That should not happen. Okay. Always address and the command should appear in the address and the command bus before the master ready is activated. Okay. The reason is the reason is always something or other data will be available in the address and the command bus. Okay. Say for example, I am trying to explain why master ready signal is activated after this much delay. After this much delay. Say for example, the bus master is activating the master uh, ready at this time itself. At this time itself. Now what? Now the one issue may happen. The issue is, see, different devices have different propagation delay. If some device is working at a faster rate, its propagation delay will be slower. It's slower in the sense it will be faster. It will be working faster. There will be less delay. If some device is working slowly, means they will have huge delay. Okay. Let us assume that D4 is working very slowly. Now, what may happen in the sense? What may happen in the sense? This master ready signal may reach D4 first before this before D4 is able to see the actual address and the command placed by the bus master, right? Okay, that doesn't mean that D4 is not seeing any address or command. No, D4 may be seeing some other old address or command which is placed in the address bus previously by the processor. What are you getting? Because always something in the processor. Currently, processor is placing this address and command at time t naught. Now say that master ready signal has reached D4 first, but it has not yet reached, but it is not able to see the new address and command placed by the processor. It is seeing some old address and command. Now D4 will assume that processor want to perform that operation and it will start doing that operation. That will become a malfunction. That will become a malfunctioning. That will become an erroneous operation. Are you getting? To avoid such thing, to avoid that such thing should not happen. For that, the bus master is delaying the master ready by this much time. Okay, are you getting? Because of that, the bus master is delaying, right? Okay, fine. So now, now from by this time, it is sure that all the devices will be getting the correct address and command. Okay, then they will decode the correct address and command. Then they will decode the correct address and command, and they will activate the. So I mean they will start. They can start decoding from here also, but the actual decoding, actual correct address. Sometimes this during this time wrong address also may be seen by some of the IO devices. But from this time onwards, it is sure that they will be seeing the correct IO device, correct address. Okay, correct. All IO devices will be able to see the correct address. Okay. So the master ready is activated at this time, right? Now, now the slave, the appropriate, now what will happen? The slave will identify the address, whichever the slave is ready, whichever the slave it is meant for, that will perform the operation. Okay. If it is a read operation, if it is a read operation, it will complete the read operation and it will keep the data in the data bus, and also it will activate the slave ready signal, and also it will activate the slave ready signal. Okay. Then during the next clock cycle at T3, master will master will stop the data. Master will stop the data and it will deactivate the master ready signal, but still this address and the command is still available. Okay. Slave ready is also still available. Slave ready is also still available, and at T5 the data will be removed from the data bus, and slave ready also will be removed. That is, once the address and the command is removed, after that also the slave will wait for some time. Okay, for one clock cycle it will wait. Then it will remove the slave ready and then it will remove the data. Okay. So this is how asynchronous bus works. At T naught, master places the address and the command information. Master asserts the master ready signal. Master ready signal is asserted at T1 instead of T naught. Okay, because of whatever the reason we discussed. Addressed slave places the data on the bus and asserts the slave ready signal at T2. At T3, slave ready signal receives the master. At T3 only, this slave ready signal receives the master. At T4, master removes the address and the command information. Okay. At T5, slave removes the data and slave ready signal from the bus. So both asynchronous and synchronous bus have their own advantage and disadvantage. Advantage of asynchronous bus is it eliminates the need of synchronization. There is no need for clock. Okay. And it can accumulate varying delays automatically using slave ready signal. Okay. But there is a disadvantage of asynchronous bus also. That is, there are two handshake. There is handshake in the sense there is a master ready, slave ready. Two things are there. Because of that, it may increase the round trip delay. So it may not be as speed as that of the synchronous bus. Okay. Data transfer using asynchronous bus involves only one round trip delay, and hence synchronous bus can achieve faster rates. Okay. Synchronous bus in the sense not the first one which we discussed, the improved one. The improved one with multiple cycles and with slave ready signal. Right? Fine. So that's it about the system bus. So let us stop here. Thank you.